evening and welcome to Tinkering with Edkelar. Previously, I took apart a Fluke 8375A benchtop multimeter. Now, let's see if there is some life left in it. Mounting the selection switches again. The front panel took a bit of off-screen cursing to fix all the screws again. Same issue as for the disassembly. There is no way, without drilling out rivets, that would facilitate a regular way. And now, adding the power supply board to validate the power rails. Weird. The rails don't quite add up. I checked pretty much all the components in the circuit for a smoking gun. And then I discovered a little unexpected detail in the circuit. The 18-volt rail regulation gets an input from the bus. Turns out that this is created from the main logic board as part of the internal 7-volt reference voltage circuit. So without the main logic board connected to the power supply board via the bus, the power supply won't supply proper power either. Sheesh! Since I don't know which other open ends might be interdependent on the device, I decided at this point to just add all the PCBs and give it a try. The ohms unit has its own power rail for current creation. The other AC line that crosses the case is for the AC test switch. Note that these are shielded lines. power on. That doesn't look good. 2 of the tubes light up, but nothing is reacting to anything. I discovered that the voltage rails are again nowhere near the expected values and that the power supply is running rather hot. To narrow down the problem, I pull some PCBs again. Finally, it's still not showing anything like a real value, but at least now all the tubes show life and the plus-minus 18 volt rails are up. After adding the boards again, I narrow it down to the AC RMS board. It seems to short out one of the 18 volt rails. And tada! A broken tantalum cap on the supply rail. 0 ohms in both directions. I replaced both of them with newer ones I had in stock. Now trying out to narrow down why there isn't any real measurement happening. The input signal seems to make its way fine through the ranging and the filter board and even arrive fine at the analog to digital converter, but then it gets complicated. The analog-digital converter is directly connected to the main logic board with a ribbon cable. No sockets, a real one-to-one connection of signals here. But how does it work? I mean, there's no CPU, no memory, and no analog-to-digital converter chip here. Well, it's very discrete. Here's what I found out, based on the online available circuit diagrams, which are blurry. After the fix, but before the video recording, I managed to get a paper copy of better quality, so I can explain stuff here. The troubleshooting was a headache though, with many connections being removed as mistaken scan artifacts. The AD converter gets the scaled input signal presented to the input pin. This is then going to the polarity detector and based on that an inverting buffer, so the actual conversion happens with the same polarity, and here's where things go slightly crazy. The AD converter takes the input and compares it with an analog reference voltage. If the voltage is beyond the threshold, the analog comparer will signal back to the control board to step on to the next one. I forgot if it's counting up or down, but same thing really. Now where does the reference voltage come from? Over here, there's what's called a ladder. It is what we know today as a resistor-based digital analog converter. Based on the counter input from the digital board, it will create a divided reference voltage. The counter stops as soon as the comparator signals, and the counted value is equal to the highest digit. Also, the current difference between the input and the reference is what has to move to the next digit. This is where the sample and hold circuit comes into play. The remaining part of the input, times 10, will then feed the same logic for the second digit, and repeat. Now that works for sampling the digits one after the other. And since the counter runs at a fixed frequency, we can say that the full sample cycle has a predictable maximum time. If it has to count all the way up to 10 for each digit, which would be an overflow anyway. Now, how about the lack of memory? Here's where it gets even more bonkers. You see, the digital section is made up of 2 counters implemented with JK flip-flops. One is the digit counter, the other is the value for that digit counter. Note that there is no digital storage. But the NICSes require constant multiplexed refreshing. and the trigger only fires ever so often? Well, here's where the difference between a sampling sequence and a display sequence comes in. When the trigger fires to start a sampling sequence, it works as previously described. But then, every analog value of each digit is put into a capacitor for storage. The display sequence will then take the digit value from there, count again for the measurement, and put the found value back into storage for a refresh. So the read-write lines will always pulse with the display, one way or the other. Analog value storage! 5 capacitors for 5 decimal digits. Modern computers need 20 bits. That is 20 capacitors for that. Now, after finally realizing how it all worked, I followed all the relevant signals and checked to see if there's activity. This finally led to the culprit. The flip-flop ICs that made up the value counters were not working. That led to the display going from some fixed random value to overload in a loop with every trigger. The parts are non-standard, however. No existing JK flip-flop has the same pinout. I found similar ones without the set input, which is thankfully not used in the Broken 2. And that's why I made some perfboard adapters. Giving it a try. Woohoo! Plausible values. Now on to the adjustment procedure. Sheesh, something is off. I can't zero out the DC ranges. The front panel has a little trimmer to compensate for tiny offsets, so that should be plus minus 30 counts. But the signal is so much all over the place that I can't tell if it's doing anything at all. So, back to troubleshooting it is. And after following the signals all over and back again, I found out that one of the relays on the input attenuator board is not closing all the contacts. So in some ranges, the input signal has no ground. That explains the wandering signal. Finally, that's more likely. It took ages to bend the contacts into shape again so that the relay would reliably open and close all of them. Now on to the alignment. And to the next problem. According to the manual, I should use the coarse DC0 on the input amplifier section to zero out the signal, but I couldn't quite get there. Again, according to the manual, if there's anything wrong on the board, I need to send it to Fluke for a replacement. Well, not sure that is going to work. It's crazy high impedance circuitry, with one trim potentiometer sending its signal into two 100 mega ohm resistors in series. So yes, if you so much as breathe on this, it'll be off. But again, after some poking and prodding, there were a few resistors to set the range of the DC trimmer that seemed factory selected, but at least 2 of them were way out of their tolerance. I put in new ones, slightly higher on one side, slightly lower on the other, and ta-da! 0 volts for shorted inputs at last. A slight mod I had to make and couldn't record was the trigger gate indicator. My unit had an incandescent bulb there, the service manual shows an LED. Must be an earlier model. Since the bulb was burned out and my replacement didn't do anything, I updated the circuit to the new version. It needed some changes. The bulb one had a driving transistor in parallel with a resistor. This way the bulb was kept warm over the resistor and flashed when the resistor was shorted by the transistor. The LED version needs a slightly different resistor in series to limit the current. Works like a charm now. The final steps in the calibration went smooth. AC, DC, ohms, all check out within specs, as far as I can tell with my means, but I'm not completely happy with the slightly empty cabinet and modded chips. I found some 4 parts PCBs with a few missing components, but they still had the JK flip-flops on them. I gave the newer chips a quick sanity test before adding them to the meter. And I also found the digital I/O boards. Again, a bit of recapping and we're in business. Here's the remote control one. And the doubled up one is the digital output unit. They both provide isolated digital signals, input or output respectively, via transformers, similar to the isolation circuitry in the calibrator. The output unit taps into a transformer winding and has its own 5V supply on it. The remote control unit needs 5V input from outside to work. But all of these boards have card edge connectors that protrude from the rear panel. I'm still on the lookout for the external DC reference board. It seems that the second empty slot never got a matching external AC reference, since the socket is listed as unused in every manual I could find. To fix the threaded inserts, I used new, metric and thus slightly larger ones and melted them into place again. That should hold slightly better than any glue at least. The top lid was covered with duct tape. The original sheet of insulation seems to have disappeared some time ago. The tape residue took ages to dissolve. Acetone made it go away, but only small patches at a time. A dab of fresh paint for the covers. To replace the missing insulation sheet, I cut up a binder and taped the pieces to the lid. Of course, after cutting the vent holes. The feet were missing again, but instead of OpenSCAD, this time I chose to put on two wooden rails on the bottom. Why? The stack of equipment where I want to put this has the same width, but is shorter, so the rear ones would dangle in the air otherwise. With the rails, I can compensate. And after slightly modifying a card edge connector, I can also give the I/O ports a quick check. Yes, it works. Now how about a Nixie meter to GPIB adapter? Maybe eventually. A funny little detail though, the external trigger input is not part of the remote control unit, but rather part of the digital output unit. I feel my upselling senses tingling. Oh, and not to forget, the ohms board has a fuse. The one that came with it was blown and the spare one was missing already. I put in a random one for testing, but now that the meter works, I splurged and got the proper one. 35 euro per piece. NASA grade apparently. Ouch. And that's it, a real gem from the early 1970s. A few repairs and some tuning and it works good as new. Oh, I didn't mention, but it even features auto ranging. Takes a bit longer to get the value though, since the analog sections need a bit of time to stabilize after switching ranges. There is an entire board dedicated to that delay. Did I mention how crazy the design seems by today's standards? Anyway, I hope you enjoyed this restoration and repair project. See you next time! With a few missing components, but they still had